because the definite integral from a to b of f of x dx represents the area under f of x from x equals a to x equals b, it's sometimes true that we can take advantage of geometry to evaluate the definite integral. So if I can look at the desired area and see that that relates to some familiar geometric shape, then that can be a quick way for me to figure out the numerical value associated to my definite integral. I'll also point out that here we're taking advantage of this area connection, but it's not always the case that you interpret an integral simply as area. There are lots of applications of integration, some of which we'll see later, but we're just at this point focusing on that kind of area connection to help us to evaluate what the numerical value of a definite integral is. So for an example, suppose we want to find the integral from -2 to 1 of the absolute value of x. We'll see later, even when we have more efficient ways to evaluate integrals, integrating an absolute value can be complicated. So we have to pay special attention. It's not so complicated when I think about geometry. So to start with, I'm going to sketch the graph of this function. So we have the absolute value of x from -2 to +1. So that's going to look like this. If I think now about the associated area, notice that I get triangles. So I have, this triangle, and we have this one. So if I can find the area associated to those triangles and add that together, that is going to give me the value of the definite integral. So coming back to this, go back to the pen. Coming back to this, I can take the area of the green triangle, which is 1/2 base times height, both of which are 2, plus the area of the pink triangle, 1/2 base times height, both of which are 1. And then we see we're going to get 4/2 plus 1/2, or 5/2. And of course, this is a relatively simple computation here. And you can imagine this could be useful for rectangles and circles or half circles as well. So kind of thinking about situations where we have a ready-made area formula that might be familiar and using that to our advantage. I'll also point out that we have to be a little bit careful. So we are taking the integral of the absolute value, which is different from the absolute value of the integral. There exist functions and intervals for which these happen to evaluate to the same number, but they're not the same thing in general, and in particular in this example we would get very different things. If we were finding what I have here, first of all, if the absolute value is the last thing we look at, we can think about what the function would look like. So we would still have the same pink triangle, it'd be 1/2. And our green triangle, which we saw has area 2, or 4/2, is now flipped below, so it's negative. So in this case, we would get that the integral, so ignoring the absolute value for now, the integral would evaluate to -4/2 plus 1/2, or -3/2. And then the last step is we take the absolute value, making that +3/2. So what I want to demonstrate here is that these are not the same thing. So you have to be very careful with notation. That's kind of a running theme throughout this course. And so what we're looking at in this example is how to account for taking the integral of the absolute value of a function. So we know that we're making the original function positive everywhere. Whereas the second case, when I put the absolute value bars on the outside, I'm not adjusting the function. You're kind of viewing this again from the inside out. First, we find the integral, and then we just make sure that our final answer is positive. So just be careful with that. That's something that, again, we'll kind of think about that distinction when we look at different objects, not just integrals, also thinking about series. The placement of that absolute value is important.